It's been a while since our last topic, and right now we'll be discussing the multiple pipe systems. Now, when I say multiple pipe systems, uh, multiple pipe systems. So, from the word itself, multiple, it means that it's more than one. Right, so it's more than one pipe. So it's a system that comprises of more than one pipe. So, for example, we have a main, um, let's say in our field, for example, we have our main line for water irrigation. So let's say we have main line, and sometimes we just wanted to have to branch the drips. Okay, so let's say this is our drip line, and then here's our plant right here, for example, and then another plant. Okay. Okay, so from the water source, then it distributes into these branching pipes. Okay, so this type of systems they're actually encountered in practice. It's also typical in the building water supply systems and even the fire sprinkler systems, and also in our field, such as in the drip and sprinkler irrigation systems. And if we also want to take a look into the internal combustion engines, we can see that this type of systems or the multiple pipe systems can also be found in the intake manifolds. Okay, intake manifolds and exhaust manifolds, and as well as in the heat exchanger systems. So they're pretty common. Okay, so in this lecture, um, we will be studying how to compute the flow rate and other data regarding the multiple pipe systems. Now, let's discuss. We have a two basic combination of a multiple pipe systems. So one is called the series, and the other one is called the parallel connection. Okay, so for the series, for example, we have a small pipe. Then it is, let's say we have some bends right here, and then we have um, an enlarged pipe. So from a smaller pipe, and then it is connected to a larger pipe. Okay, so that's one example of this series connection. For this one, for the parallel connection, we have, for example, we have our main line right here, and then we want to have a, let's say, a bypass, right? Okay, so from the main pipe that it branches into this bypass pipe. Now for the equations, they're actually the same. I mean, if we can solve a single pipe, then or let's say the equations used for a single pipe is also the same as for the equation used for the multiple pipe systems. However, there are also rules regarding the flow rates. For example, if we take into if we take in, I mean, if we take a look into this series connection, for example, we have a let's say we have our inlet right here. So let's say a fluid is actually um, going into this pipe, right? And let's say this is our pipe number one, and then this is our pipe number two. So we see that in the series connection, we see that the flow rate in this pipe one is just equal the same. I mean, is just equal to the flow rate in this pipe number two. Okay, so that's our rule number one. So our rule number one Q1 is just equal to Q sub 2, and which is just or which just means that the flow rate is just constant. Or you can just write Q total. And therefore, if this is our flow rate, then our equation for the flow rate equation, the A1 times the velocity 1 is just simply the area 2 times the velocity at 2. And let's say maybe we can just write 3 right here. Okay, so that's the rule number 1 in terms of flow rate for a series. Now for rule number 2, we have the friction loss. The friction loss H sub F. Okay, take note, this is not the friction factor, but rather the friction loss. So if we're talking about the friction loss, take note that the friction loss is or a friction loss corresponds to a 2 points. So let's say this is our point A, and then this is our point B. Then what's the friction from point A to point B? So it just says here that our friction loss at 1, or let's say from point let's say this is our point C. Okay, so from point 1 to point C, so we have each our friction loss or total from point A to point C. That's just simply the sum. So H sub 1 plus H sub 2. Okay, so this is our total head loss. Okay. Total head loss from point 1 to point 2 is just simply the head loss at 1 plus the head loss at 2. And but in terms of flow rate, we have an equal flow rate for pipe 1 and pipe 2. Now let's go to parallel connection. Okay, so for rule number 1, in terms of flow rate, then if this is our main line, okay, so the water enters here, and then it branches into this bypass. Okay, so if this is our Q total, then this will be our, let's say this is our pipe 1, and then this is our pipe number 2. So it just means that our total Q total is just the sum of the flow rate at pipe 1 plus the flow rate at pipe 2. Okay, so Q total is equal to Q1 plus Q2. And in terms of head loss, so our H, it just says that the pressure drop HF at pipe 1 is just equal to HF at pipe 2 is just equal to HF at pipe 3, and so on. Okay, so this is our main principles, or we shall say the main guidance, or not guidance, I mean the main guide for solving this type of problems. Okay, now if we have a combination of series and parallel, then that's gonna be more complex. Okay, but for us here, we'll just solve basic connections. Okay, so problem number 1, we have this problem. It says here 2 pipes, each 300 meters long, are connected in series. The flow of water through pipe is 150 liters per second with a total friction loss of 15 meters. if one pipe has a diameter of 300 millimeters, what is the diameter of 300? Uh, I think what is the diameter of the other pipe? Right? If one pipe has a diameter of 300 mm, what is the diameter of the other pipe? And also it says here that neglect the minor losses and assume an initial F value of 0.02 for both pipe. Okay, so in illustration, we have this. We have a pipe number 1 and we have a pipe number 2. So this one has a length of 300 meters, and the pipe 2, I mean the length of the pipe 2 is also given, and that's 300 meters. The diameter for pipe 1 is 300 millimeters, but for pipe 2, it's not given. Actually, that's what we are going to solve. And it says here that our flow rate is 150 liters per second, and our total head loss is 15 meters. Now, the reason why it says here assume an initial value of F of this friction factor 0.02 is simply because this is a type of problem. This is a type of problem that we don't have the. Oh, sorry. It just says here assume F is equal to 0.2 for both pipes. So it's just plainly given. So I thought that we don't have the flow rate, but here we have a value of the flow rate. So this is just a type 1 problem. All right, so I guess we can now go to the solution. Okay, so for the solution, now our first step is recall the rules. And since this is a series connection, then our total flow rate is just equal to the flow rate at pipe 1, which is just equal to flow rate at point 2. And our flow rate is given in terms of liters per seconds, and we have to convert this in terms of cubic meters, cubic meter per minute, which is cubic meter per second, which is just simply 0.15. Okay, and our head loss, HL or HF. Okay, our head loss is simply H from pipe 1 plus the H. The head loss at point or at pipe 2. And our relation here we have H1 plus H2. Since the head loss is given, this HF or HL, we can just write HL, 15 meters. So 15 meters is equal to H sub 1 plus H sub 2. And we can write this as equation, let's say equation 1. Okay, now if we have a complete data of the geometry of the pipe plus the friction factor, then we can actually solve for the head loss at point 1. Okay, so H1 we can solve because the pipe diameter and then the pipe length is given, plus the velocity. We can actually solve that using our flow rate equation, which is Q is equal to area because we have the diameter, so we can solve for the area times the velocity, right? So I guess the next step is to solve for head loss at pipe 1. Okay, so H sub 1 is equal to F L over D times V squared all over 2G. Okay, what is our F? That's 0.02. Okay, our L is 300 meters, and our our diameter should be expressed in terms of meters. So that's 0.3 meters, okay, times the v squared, which is just simply recall this equation. Q is equal to AV, and therefore V is just Q all over A. So Q squared, that's just or we'll write it here. I think we'll write here solve for V1. Okay, so V sub 1 is just simply Q sub 1 times divided by the area at 1, and we have a 0.15 meter cube per second divided by the pi d squared all over 4, and our diameter is 0.3 squared all over 4, and we have a value of 2.12 meters per second. Okay, so here we can substitute 2.12 meters per second, and this one is squared divided by 2 times the 9.81 this meters per second squared. Okay, and if we do the computation, what we get is a value of 4.59 meters. So let's write here a sub 1 is equal to 4.59 meters. Okay, so right here we'll also box this equation, and let's call this equation number 2. This is equation number 1. Right. Okay, now we have H1. We have this total head loss, we have the H1, then we can solve for H2. And once we have the H2, then we can solve for we can apply the Darcy-Weisbach equation, and we can solve for the diameter. Okay, so this is step 3. Now this is step 4. So substitute equation 2 to equation number 1. Okay, so if we substitute that, what we get is 15 meters minus 4.59 meters is equal to H2. H2 is equal to 10.41 meters. Right, this is our equation number 3. Now, since we have this, then we can solve right here. We can now solve for the 2. Okay, so our working equation is H sub 2 is equal to FL over 2 times V squared over 2, oh sorry, FL over D times the V squared all over 2G. Okay, so let's express this. Let's express this in terms of the flow rate and then the area. So FL over D times, this is 1 over 2G, and times the Q squared all over the area squared, right? So this velocity is just equal to Q all over A, but since this velocity is squared, then we'll square the numerator and we'll square the denominator. Okay, now we can express this area in terms of diameter. So therefore, FL over D times Q squared all over 2G times pi, right? Pi D squared, right? This is pi D squared all over 4, but this term right here is still raised to 2. Okay, so therefore this will be d to the fourth. Okay, so d, or we'll write it again here. So we have um, okay, so we have 2g all over, this is 16, right, times d to the fourth, and therefore we can have FLQ squared all over d to the fifth times this constant. Okay, so that's 2 times 9.81 divided by 16. And if we write that in the denominator, we have 1 divided by the answer. We have 0.81. I guess we also miss, by the way, I guess we also miss something here. We should have pi squared as well. Right, so that's gonna be 2 times 9.81 times squared of the pi divided by 16. Right, 1 divided by the answer, we have 0.0. So we have a value of times 0.0826. Right. Okay, so if we write here, our equation would be h sub 2 is equal to 0.0826 friction factor times L times Q squared all over D to the 5. Okay, so this equation would also be useful um, if we have the flow rate that's given. Okay, so since in this problem we are here solving for D, then therefore this will be D raised to 5 is 0.0826 times our friction factor, that's 0.02 times the length, which is 300 meters, times our flow rate of 0.15 meter cube per second. This one squared, right, divided by the head loss at pipe number 2, which is 10.41. Okay, so now let's compute times 0.02 times 300 times 0.15 squared divided by 10.41, and we have to take the fifth root of the answer, and that's 200. Our D is 255 mm. All right, so this is our answer. Okay, so just to have a review, we have this problem that's a multiple pipe systems in series, and the pipe number 1 has a diameter, the length, but the pipe number 2, we have to find the diameter, but we are given the flow rate and also the total head loss. So first, what we did is to recall the rules for series connection, and we know that the flow rate is just equal to the flow rate at 1 is just equal to the flow rate at 2. It's just simply the total flow rate. Okay, and since we have that, we just converted the flow rate from liters per second to meter cube per second. Then we also apply the second rule about head loss, and we know that in series connection we have the total head loss would be simply the sum of the head loss at point 1 plus the head loss at point 2. Okay, so since we have this, we have two unknowns, right? So we need two equations. Two unknowns, we need two equations. So for h sub 1, for the head loss at 1, we can actually solve that using the Darcy Weisbach equation because we have complete data regarding this pipe number one. So we have the diameter, so we can solve for h sub 1, right? So that's what we did in this step number 3. So solving that, we have 4.59 meters. Now since we have h sub 1 and we have this equation 1, then we just have to substitute this h sub 1 into the equation number 1 to get the head loss at pipe number 2. And once we have this, we can apply the Darcy-Weisbach equation to solve for the D. However, we did some derivations of this head loss as a function of flow rate instead of a function of the velocity. Okay, because velocity is also a function of diameter, so therefore we can just um, rearrange this equation in terms of diameters. Okay, so we did the derivations, and we have obtained this expression that the head loss is just simply the friction factor times the length times the square of the flow rate divided by the fifth power of the diameter times this constant 0.0826, which is just simply the product of this 2g times pi squared divided by 16, and we take the reciprocal and we obtain this 0.0826. Okay, so we have this expression and one equation, one unknown, so we can solve for D, and the D is 255 mm. All right, now um, I guess we will do another problem for pipe in a parallel connection in the next video.